welcome to another episode of The Shot with Cosmos. Cheers to the mystery of the sun's corona.
Well, cheers.
Yeah, I was going to say, what's the tink at?
The one time I remembered the table bump, the table tink, and not in-person tink. Anyway, the sun, as we all know, is a mass of superheated gas, as some would say, or sing, a gigantic nuclear furnace.
Thank you so much. I was about to interject.
A little they might be giants for everybody out there. So inside the sun, you have your core. That's where your nuclear fusion is happening. That's what's generating all that energy that we see as light and feel as heat. You have the radiative zone and the convective zone after that. And that's the inside of the sun.
It's a big onion.
It is a big onion, which all stars are basically onions throughout their lives.
Yeah, but only like 3 or 4 layers.
Oh, yeah. More layers you get, though, than the closer to death you are if you're a star.
Yeah, that's true.
So beginning the outer layers, you would think that it starts off pretty normally with the sun, with the photosphere. This is the visible surface of the sun that we see.
And how do you remember it's called a photosphere, Liz?
Because you see it and take a picture of this, so I don't know. How do you remember?
I don't know. That's basically the photosphere is the part that we see, like a photo.
Yes.
I thought maybe I got that from you.
I don't know. I think I got that from maybe my astronomy classes.
Didn't get it from me, so it wasn't in me.
So it's the visible surface of the disk that goes to about 250 miles up from.
Okay.
Up. It's outer layers of the core.
That's nothing for the sun. 250 miles.
Surface. It's the surface of the sun. If you.
That really is a very thin skin, onion skin.
Mm-hmm. And it goes from in temperature range from the bottom of the photosphere, the deepest level of this photosphere, 11,000 degrees Fahrenheit, to the outermost layer, which is about 6,000 degrees Fahrenheit.
Spicy.
So it cools down, which you would naturally think
really
is
fast.
Correct, right?
Yeah.
Like the further away from the core you are, then the cooler things get. However, something crazy happens. We got a little weird. We got a little mystery happening with the sun. After the photosphere, you get the chromosphere.
Okay.
And that's about 250 to 1,300 miles above the photosphere. And things go from 6,700 degrees Fahrenheit to 14,000 degrees Fahrenheit. Things get hotter.
So I guess since the photosphere is cooler, I guess truly the closer you are from danger, the farther you are from harm.
Oh.
All right. Now we get the transition region. This is kind of like a 60-mile narrow region where temps go crazy. They skyrocket from 14,000 degrees to 900,000 degrees.
Wow, almost a million degrees.
And then as you get into the corona, this is the outermost layer of the sun. It is 1,300 miles above the surface. It can't be seen with the naked eye, except during a solar eclipse.
A total solar eclipse.
Mm-hmm. And then you kind of see this extra sort of atmosphere. And I would say, you kind of almost depict that in a way with like when you draw a picture of the sun and like the rays coming out of the sun.
You get the spooky rays coming out.
Yeah, it's kind of like.
Or the friendly rays.
It's kind of like that. The ones that'll kill you instantly because they're super energetic and hot.
And a million degrees.
A million degrees. So it's weird. This is a weird thing that things get hotter the further away from the core you are, where the core is, how hot is the core again?
It's tens of millions.
Tens of millions.
20 million.
I would say 28 million, I would say.
Yeah, something like that, okay? So it's very hard to study the sun. There are really kind of 2 ways to study the sun. There's remote, using a camera positioned further away from the sun, studying the sun at different wavelengths of light. And then you have an in situ method, which is basically where a spacecraft can get close, can fly through the particles of the sun and measure the particles and the magnetic activity that way. So what was done is Daniel Toloni with the I'm sorry, Federico. With the Italian National Institute for Astrophysics, he used the ESA Solar Orbiter and NASA's solar probe. Now, the solar orbiter, that can do remote and in situ measurements, whereas the Parker Solar Probe, that is for like close in situ measurements. So
it's moving
So it
fast.
gets very close. It goes very fast.
it gets very close. So it can really study kind of like the fine details of those particles in the sun, whereas the ESA's solar orbiter, it can look at more of a large scale measurements. And so what they wanted to do is use both of these. They've never been used at the same time to collect simultaneous measurements, where they can study like the close-up effects on particles using kind of what's happening at a large scale of the sun. But they had to do some crazy dancing with the spacecrafts because they needed a certain alignment. And so they got approval to actually have the Parker Solar Probe roll 45 degrees and point just a little bit away from the sun so that it could get into the field of view of ESA's solar orbiter that has a coronagraph called the solar metis on it. And so they could study the coronagraph simultaneously as the Parker Solar Probe was collecting data on what's happening with the particles that are going on there. And so this was the first time that they've ever gotten simultaneous measurements, and the data showed that solar physicists have currently been correct in what is going on. And what is going on, they believe, is that turbulence is actually a way of transferring heat. So what that means is that stimulating movements of fluid, gas, or liquid, energy is transferred to even smaller scales. Like when you stir a cup of coffee and you're stimulating those particles, the energy is transferred on smaller scales into heat. And so basically the fluid for the corona is also, this plasma of the corona is also magnetized. And so the magnetic energy through this turbulence is also transferred into heat. And so that is why it is able to it gets hotter, because there's a lot more turbulence happening out there in these outermost layers of the sun.
So does that mean that the corona gets hotter when the sun's at a maximum with sunspots?
I don't know. More data is needed. These are the preliminary observations that are in the astrophysical journal letters published under coronal heating rate in the solar wind. So more data is needed, but this is like really kind of the first kind of like observational conclusive evidence using these two spacecrafts combined that is showing how the turbulence there are because of using Parker, they can look at it's primarily how these photons are or I'm sorry, did I say photons? It might be, I think I had it in my notes somewhere. It might have been protons. I don't know. But basically how they're able to heat up more, whereas you would think they would cool down. But it's because it's a violent place out there by the sun. It's not just getting hot in there, it's getting hot out there.
Damn, that's true.
Bosh. Anyway, that's The Shot with Cosmos. Thanks for joining us, everyone. We'll see you next time. Follow us on all the things at Drinking Cosmos or Cosmos with Cosmos. Peace. Live long and prosper.
Cheers.
Stay cool.